All right, so today we're going to ask the fundamental question, how far does classical mechanics survive inside of quantum mechanics? And, the answer kind of lies in this, this indestructible bridge between quantum phases, tunneling exponents, discrete spectra. But the full, algebraic structure of these classical observables cannot be perfectly lifted to quantum operators due to operator clustering. Operator ordering. God, sorry, it's late. But the classical world is going to survive as a skeleton of this of action processes, and quantum mechanics is just going to add deformations of order h bar and beyond. So let's get specific. We can talk about the classical algebra that kind of survives with Poisson brackets. And canonical quantization. All right, so in classical mechanics, you have a phase space with Q and P that carries the canonical Poisson bracket. Where if I took the Poisson bracket of F and G, this is the partials, kind of the difference of their partials kind of mixed together here. All right, and that should be a P. All right, and of course we define Q and P in phase space. The Poisson bracket of these two should be 1. And now what quantization is going to do is it's going to try to map real functions, Q and functions of P and Q, to Hermitian operators. And these Hermitian operators are some representation of F on a Hilbert space, such that we take F and G and map this to IH bar times the commutator of these operators. This should be generally review, but for basic coordinates for Q and P, this works very nicely because we're left with the commutator being expressed as such. So now what we can do is actually test a higher order bracket. So let's say we have Q3 and P3 being a partial derivative of Q3, P3, P. Well, if we were to compute this, this would be 3Q2 times this, which is 9Q2P2. And if you have a quantization map, for this to be a homeomorphism, that would require that the operator for Q cubed and P cubed should be equivalent to 9 times Q of the representation of Q squared P squared. Now we need a precise way of ordering or prescribing this ordering, and so the natural way of doing this is called Weyl ordering. Or, symmetric ordering. So if we just say we want to do the representation of q to the r and p to the s under the Weyl ordering, we would have the formula for this. For the sum basically the sum over all of the permutations of the RQ hats and SP hats. Okay? So for Q2, P2, we get Q2, P2 to be equivalent to, just applying the formula here, 1/6, and then just taking all of the permutations over that. So we would have Q hat P hat squared plus Q P Q hat P hat plus Q hat P hat squared Q hat, let's keep going down here, plus P hat Q squared P hat plus P hat Q hat P hat Q hat plus P hat. All right, there we go. So that's just how we would choose to have a nice symmetric ordering for this particular case. Now, if we want to compute the commutator of P hat Q hat to the cubed, 1 over H hat, or sorry, 1 over H bar, using this canonical commutator, Q hat P hat is equivalent to IH bar, we can repeatedly commute the factors. And so let's just move up here. And so by repeatedly commuting the factors, P hat to be Q hat P hat cubed minus P hat cubed Q hat cubed. This should be equivalent to Q hat squared plus Q hat P hat cubed minus P cubed Q cubed. And what we could do is take advantage of a formula systematically by taking a n. If we were to take the nth, if we were to do the nth commutation with a, this should give us a n minus 1 times the commutator of this when AB commutes with A. We would use that, but this is not a scalar. So it's a number, I hat, basically, or a type of number, and well, it does commute with both Q and P, so we can treat it as a constant during the commutation. So if we repeatedly apply that this is equivalent to this, it can yield uh, 9 H bar of P. And this would be a different operator. We would use the symmetric operator. And the symmetric operator is basically this precisely, it's the Weyl ordered one up to some overall constant. So the extra term here, this extra term comes from the double commutators that we would have. And so if we were to divide out everything by IH bar, we would be left with uh, 9W Q squared P squared plus 1/3 of H bar squared. But the direct quantization of the Poisson bracket without the HQ term here would hence show us that Q cubed and P cubed is not equal to the Weyl ordering. And hopefully it's not hard to see that of these three, of this representation of this Poisson bracket there. All right. Now, the physical meaning of this is that this allows us to delineate between linear quadratic observables which are just polynomials of total degree less than or equal to 2. The quantization map can be made a Lie algebra isomorphism. So for cubic and higher observables, the operator ordering ambiguities necessarily introduce corrections of H bar squared and higher. So this is called this is formally called the Groenewold van Hove obstruction. Okay, and it's very foundational because it tells us that there's no globally consistent quantization that preserves the Poisson bracket for all classical observables, and that the classical world survives only in the limit as H bar goes to 0. And for any finite choices of H bar, the correspondence is approximate, and genuine quantum effects like the H bar squared term start to creep in. So now what we can do is talk about the WKB approximation. And the WKB approximation just tells us to first start with the particle of mass m and energy E particle in a one-dimensional potential, so just V of x is a potential. The classical momentum will then be P is the square root of 2m E minus Vx. Okay? And in the classically allowed region, let's say where we only take, basically we're restricted to have positive energies, the WKB wave function will take the form of 1 over the square root of the momentum times the exponent of I over H bar integrated from P x. Okay? And this exponent here is the classical action divided by H bar. And so this quantum oscillation will be controlled by this same phase factor that governs classical motion itself. All right, so this is the relationship between classical and quantum mechanics. Now, what we can try to do is talk about the notion of analytical continuation. Now, analytical continuation says that when the potential is greater than the energy, the classical momentum will become purely imaginary. And so the momentum will become imaginary, where this k function here is the 2m v of x minus e. So we just kind of flip the inside of that difference by making it imaginary. So that's what the momentum is. And the WKB approximation will be obtained by the analytical continuation so that the exponential oscillatory factor turns into exponential decay. So we'll have that 1 over h bar is the integral of 1k dx, which is equivalent to e to the minus h bar of kappa, or k, dx. Hence, in the barrier region, in some barrier region, a region between turning points, the wave function amplitude becomes, whenever the action, where we've analytically continued it, with this action being, the wave function amplitude is just suppressed by this, sorry, that was my alarm, again, but it's suppressed by this factor, and this will be equivalent to the integral of x1, x2 times the square root of 2m vx minus e dx. All right? So now what we can do is talk about the tunneling probability. And the tunneling probability will just be given from being approximately e to the minus 2h bar from x1 to x2 of the square root of 2m v of x minus e dx. Why? It's basically it's just the probability of transmission through the barrier as this squared amplitude ratio, giving this WKB formula. All right. Now, what we can do is actually take the potential. We can take the potential to be this kind of inverted parabolic type of barrier, or in other words, simple harmonic oscillator. But we can say a parabolic barrier with the top at this particular value, and for the energy that's less than the initial potential, the turning points are equivalent to plus or minus 2v naught e over m omega 2, or omega squared. And then the exponent integral becomes the square root of 2m v naught minus e minus m squared omega squared x squared and dx, right? And if you take the variable u to be mwx over the square root of 2m v squared e squared, you can recognize that that is the area of a semicircle, and obtain, that should be an S, sorry, and obtain that the value of that integral is pi omega. All right, pi v naught e over omega. Therefore, the tunneling probability is going to be approximately e to the minus 2 pi v naught e over h bar omega. Okay, so that's the exponent. So the classical action is in the forbidden region, and that same action would appear in the phase. Now it governs the suppressed exponent. So a wide low barrier and narrow tall barrier have the same identical suppression integral. Thus, this has identical tunneling probabilities. Now, lastly, what we can do is talk about the classical action and how this classical action predicts quantum energy levels, like a bouncing ball system. So let's first look at the bouncing ball. So if we consider a ball with mass m again, bouncing vertically in a uniform gravitational field, G, with a perfectly rigid floor. Okay, so the floor is rigid at z is equal to 0. The potential itself will look like just mgz, with z being greater than 0, and an infinite wall at z equals 0. Now, if we're given an energy, for a given energy E, the upper turning point is going to be E over mg, because the particle moves from z0 to z max, and then, and back, and tracing this closed orbit in phase space. Now, the action around one full cycle of this in phase space will be the integral of the momentum. It would be a full closed circular integral in phase space from 0 to z max to m e minus mgz dz. And if you let u be e minus mgz, then dz is equal to minus du over mg. Then this closed phase space integral will then be equivalent to the square root of 2m over mg from the integral from 0 to e, the square root of u du, which is equivalent to 2m over 3mg e to the 3 halves, right? And now what this allows us to lead to, now that we have this closed kind of action, the classical action integral through for the full cycle, for a bound state with two soft, we'll say soft classical turning points, we can note that let's just work with general coordinates here. We can note that there's something called the Bohr Sommerfeld condition, and what it tells us is if we take the full cycle, this should be equivalent to 2 pi h bar times n plus 1/2. However, the hard wall at z is equal to 0 it imparts this imparts a phase loss of 2 pi, or pi over 2 per reflection. All right, so the wave function must vanish there, and that effectively shifts the quantum number by 1/4. So the correct condition for one hard wall and one soft turning point would be pzdz of 2 pi h bar n minus 1/4, for n is equal to 1, 2, 3, etc. And if you choose n to be a positive integer, that gives positive energies. Therefore, if we want to equate the classical action to the quantized action, so this is the quantized action here, and then this is the classical action, what we can do is just take the results and set them equal to each other, because the classical and the quantum are equal to each other in this particular model. That is the assumption. It's called the semiclassical quantization. And solving for En, we just kind of write out 3 pi h bar g over 2m 4 times n minus 1/4 2/3. And this exact quantum problem reduces to something called the area equations. So the eigenfunctions for the area equations, or the eigenfunctions, are the set of area polynomials with lambda n, with L here being h bar over 2 m squared g to the 1/3. And these eigenvalues come from the zeros. All these eigenvalues come from the zeros of the area function, which would be En is equal to lambda n mgl. And the asymptotic zeros, so asymptotic zeros of the area function are given approximately by 3/2 pi, all of this to the 2/3. 3/2 pi n minus 4, all of that to the 2/3, which, if you were to substitute in, z is equivalent to E in over mgl. That would actually reproduce the WKB result. So that's the classical integration integral that dictates the quantum energy spectrum. Only quantum input is the phase shift, counting that value of h bar itself. So it's just the quantum input that allows that phase shift. So now we can really see this unity. We have a nice perspective and pretty picture that makes sense as to what quantization is really about. This classical action, S is equal to P dq. This appears with different quantum roles. Of course, it's the real action, so it gives the phase of e to the is h bar in WKB wave functions. and it controls. This actually controls, or the phase itself is controlled by the action, by the real action, and it, it controls interference and propagation. Oh, sorry. Now, the imaginary action, where we just take the integral of I to the kappa dt, this gives us the tunneling suppression, and that's obtained by the analytic continuation of the classical motion. And then the closed orbit action, this becomes a quantization condition. Oop, I'm about to die. But that selects discrete energies from the classical phase space area. All right, so it selects En from classical phase space. All right, so that's really important to get right. And the classical Hamiltonian dynamics provides really the core of quantum mechanics. But the algebraic structure of the observables can't be lifted identically, because again, the Grunewald von Hove obstruction shows us that for polynomials of degree, so for polynomials of degree greater than 3, the Poisson bracket acquires these higher corrections, where if we take the operators and if we want to take the operator from the Poisson bracket, it's going to acquire higher order terms in h bar squared. So the operator ordering introduces this unavoidable classical terms, and the classical world survives perfectly only in the limit as h bar goes to 0. Hence, this thing needs to go away for it to actually work. So quantum mechanics, at finite h bar, quantum mechanics deforms the classical algebra. So really, the central message of this, if you take away anything, is that quantum mechanics doesn't replace classical mechanics, it just builds upon it. So the classical action is the key that unlocks tunneling and spectra and wave propagation. And the entire semi-classical regime, so the WKB and Bohr-Sommerfeld quantization, it's nothing but classical mechanics with added bookkeeping of phase. And the quantum theory, you can think about it as containing genuinely new information beyond the classical Poisson brackets that we have here. The operator ordering that we went through, non-commutivity, these introduce corrections that can't be encoded with any perfect quantization map. So you can think of classical action as this, again, as this universal bridge between everything, of course, and the full classical algebra is really only an approximation or an approximate shadow of the quantum commutation relations. Okay? So that's really everything that we have so far. And I will see you guys next time.